Hello everyone. My name is Harshang Chaudhary. I am currently in the final year of my BTech degree in Metallurgical and Materials Engineering at National Institute of Technology, Raipur, India. And today I will be presenting my work on high strain rate response of nickel-based superalloys using split Hopkinson pressure bar. And I will also show you the simulation of this setup via MATLAB code, which will give you better understanding. So let's start. Yeah. So this is my overview, which I will follow. So first understand the basic fundamentals of stress strain curve because it is important to understand the basic of mechanical metallurgy to understand how this material behaves under different loading conditions. Now, yeah, you can see in this curve, engineering stress strain curve, till this ill point, there is an elastic region in which when material deforms, it will regain its original shape. But after this point, it enters in the plastic region. And after the deformation, it, it will not able to regain its original shape. So this deformation is permanent deformation. And the maxima of this curve represents ultimate tensile strength at which necking begins, followed by this fracture point. At this point, the material will leads to failure. And you can see this graph represents two stress strain curve, where you can see after this UTS point, the value of stress will be increasing. So what is the reason behind this? So reason is in the two stress strain curve, it will take actual instantaneous area, and engineering stress strain curve considers original cross section area. And here I have mentioned the conversion between engineering stress strain curve and two stress strain curve. Now let us go ahead. Yeah. So now we will understand how the flow stress affects the plastic deformation or how this material resists the plastic flow. Now I have this stress strain curve here. I have this elastic region which is represented by this red line, and I have this plastic region. So it can be written in mathematical way as sigma is equal to k times epsilon to the power m, where k and n both are material constant. It means it depends on which material you are deforming. So based on their values, there are three curves. The first one is rigid ideal plastic curve. Second is ideal plastic curve, and this is strain hardened curve. And for the most of the metals, this value of n varying from zero point 0.1 to zero point 0.5. So what is this deformation basically? After the as I increase the flow stress, the value of strain is increasing. So basically this phenomenon is known as strain hardening, due to which what happens as the material undergoes into deformation, the dislocations are created and it begins to move. Initially, they are freely to move, but as the plastic strain continues, what happens is this deformation gets intersect with each other. And here you can see in this figure, the dislocations pile up along the slip lanes. So you can assume it like the traffic jam along a certain slip rails. And in this second figure, you can observe that a dense network of dislocation form along the grain boundaries, and this is known as dislocation forest. And as I already discussed, that as you increases the strain, the with respect to it, the flow stress will also increase. And this concept is nothing but strain hardening. Now let us move ahead. Yeah. Now we will see how this temperature affects the flow stress value. So as I as you can observe in this curve, this stress strain and this stress and respect to this temperature curve, you can see as I am increasing the temperature, what happens is this flow stress value will be decreasing. And but in this region, what happens is you can observe a small hump. So what is the major reason behind this? So it happens because of dynamic strain aging. So what is dynamic strain aging? So dynamic strain aging is nothing but the diffusing solute atoms temporarily block this dislocation moment, and due to which it makes deformation harder before thermal softening overtakes. So as you can see in this thermal softening curve, at different temperature, you can see at same strain, it produces low stress. So this is the concept of thermal softening. So why this is so? This is because of recovery and recrystallization. It will leads to decrease of dislocation density. Here you can see with the help of this microstructure, you can observe that as I'm increasing the temperature, the the dynamic recrystallization form along the grain boundaries, and due to which this dislocation densities are decreases, right? Yeah. Now we will see what is fatigue. So fatigue is a material failure which is due to repetitive loading. Now here in this SN curve, you can observe here this fatigue limit. So what is this fatigue limit? It is a limit below which material can undergo infinite cycles of failure. And you can see this mild steel can show a fatigue limit, but the non-ferrous metals like aluminum can undergo infinite number of cycles, and eventually after it will fail. So there are two types of fatigue. One is low cycle fatigue and another one is high cycle fatigue. Here I already mentioned it. And what this curve tells. So you can observe here at low cycle fatigue, the value of stress is very high as compared to this high cycle fatigue. So due to which the initiation of crack, it will lead to catastrophic failure. And these are the several factors which affects this fatigue behavior. Now, here comes the most important part of our presentation, which is split Hopkinson pressure bar. So what is this setup? This setup is generally used for dynamics loading, in which the material undergoes high strain rate, typically between 10 to the power 2 to 10 to the power 4 per second. So the major components of this setup are gas gun. Here this bar is nothing but striker bar. This is the incident bar and this is the transmitted bar. So what happens is when we pressurize this gas chamber here, this is the gas chamber. So due to pressure difference, this tracker bar propels and it will hit this incident bar, due to which as you can see our sample is held in between this incident bar and striker bar, due to which when this striker bar hits this incident bar, the sample will gets compressed, and in that the uniaxial stress wave phenomena takes place. And here you can observe at this end and at this end of this incident bar and transmitted bar, there are two strain gauges which are connected in half opposite arm Wheatstone bridge setup. So what is half opposite arm Wheatstone bridge setup is, it is used to reduce the effect of bending. So what is bending? Basically, the bending creates additional strain and it will affect our final result which you don't want. So here you can see this is the Wheatstone bridge. It reduces the effect of bending here. And now here you can see one formula. This formula is known as strain gauge calibration. It is used to convert strain signals into strain. And here you can see one furnace. Yeah, you can also carry out this test at elevated temperature also. So you can hold that specimen with the help of thermocouples inside this induction furnace. Now, let me show you the simulation of this setup. So just a second. Yeah. Now, in this code, I have created some synthetic signals for incident, reflected, and transmitted with the help of these formulas. And there are two channels basically. So first channel is connected to incident bar, and another one channel between incident and oscilloscope, obviously, and another one is connected to transmitted and oscilloscope. So when I will run this code, then you can see the graph is generated between signals and time. Now this is the transmitted signal, you can see here, and this is the incident signal. So what happens is when the strain, when these signals are propagate via the specimen, some of gets transmit into transmitted bar, and some of gets back reflected, and which can be measured with the help of this strain gauge. And with the help of strain gauge calibration formula, you can easily convert strain signal into stress strain curve. So here I consider some constant. That wave speed is 5,000, and here are the dimensions of that setup bar. And the setup bar, the bar is made of margin steel 300. Yeah, when I will run this code, yeah, you can see this is the stress strain curve. Now, what happens? Sometimes the additional irrelevant signals are also generated due to noise or any other reason. So I have also created some disturbances. Wait, let me show you. Yeah, so these are the disturbances which I have created, and it will affect our result. It will leads to creation of these spikes in the signals. And when I will add these signals in the main results, you can see it will affect our final stress strain core also. Yeah, you can observe here. It will create signal spikes here, right? See. Now let's get back to our presentation. Yes. Now I have the data of aluminum 6063 in T6 condition. Now, when I carried out SHPB test without any specimen, you can clearly observe that all the waves which is coming from that incident bar is completely transmitted to transmitted bar, which is why this is so, because there is no any specimen is held in between these two. So all the waves are gets completely transmitted into this transmitted bar. And you can observe here this C is nothing but this compression signals are there, because our specimen gets compressed between these two bars. So these incident signals are compressive. And when I carried this test with cylindrical aluminum sample of AL6063 in T6 condition, you can see the incident compressive signal gets some of gets transmitted into transmitted bar, and some of gets reflected. Yeah, here you can see that. And also you can observe here few spikes. It is nothing but the noise or any disturbances in our main result. But we don't want this result. We only want this result. Okay. So, and also the application of this are, as I already told you, that this setup is used at high standard testing. So it is used to analyze the failure mechanism under dynamic loading, and it evaluates the armor grade steels also. Now let's talk about nickel-based superalloys. So these alloys combine high temperature strength, excellent corrosion and oxidation resistance, high thermal stability, also excellent thermal fatigue resistance, which makes it ideal for working at high elevated temperature. And as you can observe the microstructure of these superalloys, so basically there are three major phases. First one is gamma matrix, gamma phase, which is a matrix phase. Then next two are gamma prime and gamma double prime, which are precipitate phase. And here you can observe in this microstructure, there are periodic like structure along the grain boundaries, which is nothing but which is the intermetallic phase here. And now let's talk about their crystal structure. So gamma phase is ductile and it has crystal structure of FCC, and this gamma prime has composition of nickel and aluminum. It is Ni3Al. So this crystal structure is L12. See, it looks quite similar to this FCC, but it has L12 structure. It is highly ordered structure, and that's why it is also known as superlattice. And here you can see the structure for gamma double prime phase, which is BCT. And when it comes to this volume fraction, so this gamma prime phase is uniformly distributed within the gamma matrix, and this it will contribute around 50 to 60% in the macrostructure, and for this gamma double prime phase, it will it will contribute around 10 to 30%. Now, these are several application for these superalloys. Now, let us talk about nickel-based superalloy, specifically SO263. So, uh, here you can observe this macrostructure. So, you can see only two phases are there. One is gamma matrix phase and another one is gamma prime phase. So, gamma double prime phase is absent here, and also some intermetallic phases are present here. Now, it will leads to create it will provides high creep resistance to our alloy, and these gamma precipitates are responsible for providing high corrosion and oxidation resistance also. Now let's talk about the mechanical behavior of this material. So at low strain amplitude, the gradual hardening takes place, and at high strain amplitude, rapid hardening takes place. Now, you can observe here this plot, which is nothing but CM plot. CM stands for coffee mention plot. It is a way of presenting low cycle fatigue. Now, as you can see, this at this elastic region, the strain is low, and at this low strain, the fatigue sorry, this life is very high as compared to this plastic region. And after this point, this elastic mechanism transform into plastic mechanism. So this point is known as transition point. Okay, and these are the composition for this superalloy, in which the nickel is present around 50 to 60%, and which will be balanced by these alloying elements. Yeah, now we can see that this strain rate increases at this 923 Kelvin. You can see this flow stress and yield stress both are increasing. Right here, you can observe that this both are increases. This is because this strain rate gives less time for thermal activation. And when it comes to this microstructure, you can see at 673 Kelvin, you can observe a more defined fracture features, and also with limited plastic deformation. And at 923 Kelvin, you can see these fracture features are ductile. Right. Now, this is the pictorial representation of SO263. during SHPB testing. So initial microstructure of this alloy in aged condition, you can clearly observe that these gamma precipitates are uniformly distributed within the matrix. And after SHPB, you can observe that this gamma precipitates is partially dissolved in within the matrix, and this dynamic recrystallization forms along the grain boundaries. And this is the signal time graph of SO263 after SHPB testing. Here you can observe this graph, and basically this SO263 alloys is majorly used in uh, jet engines, specifically at combustion liners, nozzles, afterburning section, and turbine blades. Now let's come to its conclusion here. So as we discussed, this SSPB effectively works at extreme loading conditions, typically between 10 to the power 2 to 10 to the power 4 per second to study the dynamic material behavior. Also, as our study says, this material exhibits low cycle fatigue and high cycle fatigue characteristic, which are influenced by this microstructure, temperature, residual stresses, and corrosion. And here are few references which I have used. Yeah. So this is all about our today's topic. Thank you so much.